Why does your body hurt before it rains? A question that seems very simple. You have experienced it countless times. You wake up one morning with a slight ache in your knees. One afternoon your back stiffens for no clear reason. A headache arrives before the clouds even gather. You sense that something is changing even when the sky is still clear. But why? Most people do not really ask the question. They just accept it as a habit of the body. Or worse, they are told it is only a feeling, only imagination, only coincidence. But if you pause for a moment and think, if this repeats dozens or hundreds of times in your life, is it really random? Or is there some mechanism quietly at work that we have not yet seen? This is where things get interesting. Because when you start digging into this question, you are not just talking about joint pain or weather anymore. You are touching fundamental laws of physics that have existed for hundreds of years. And once you see them, you realize that feeling is not vague at all. It is real. It can be measured. And it is happening inside you right now. To understand that, you have to start from a truth very few people think about right now. As you sit still and listen, your entire body is under enormous pressure from the atmosphere. At sea level, average atmospheric pressure is about 1,305 pascals, or about 14.7 pounds per square inch. And that number is not small. It is equivalent to a column of air nearly 100 kilometers high from the Earth's surface to the edge of space, pressing down on you from every direction. If you add up that total force over the entire surface area of your body, you are bearing a load of several tons. But you feel nothing. No sensation of being crushed. No feeling of being squeezed. And the reason is not that the force is small, but that it is perfectly balanced from inside. The pressure inside your body, in your blood, in your tissues, in your joint fluid, in the air you breathe into your lungs, and even the gases dissolved in your body fluids, has all adapted and balanced with the external pressure throughout your life. You exist in a state of dynamic equilibrium that you almost never notice. It is like a fish swimming in the ocean not feeling the pressure of the water, because the pressure inside its body is also balancing exactly with the surrounding environment. But here's the important part: most people miss this balance is not permanent. It only exists when the environment is stable. And the environment is not stable. The atmosphere is not a static layer of air. It is always moving, always changing, always fluctuating with weather systems traveling across the planet. Pressure can drop or rise in just a few hours when a weather front passes. And when that happens, the perfect balance your body maintains begins to shift. Not instantly, not evenly, but enough to create a difference. And it is precisely in that small difference that your body begins to react. And to understand exactly what happens in that small difference, I want you to go back in time to 1662, when an Irish scientist named Robert Boyle published one of the first and most beautiful laws of gas physics. Boyle did nothing mystical. He did not need giant machines or modern computers. He simply used a J-shaped glass tube, trapped a column of air at one end, then poured mercury into the other end to change the pressure acting on that trapped gas. And what he observed was so simple, it was almost shocking. When pressure increases, volume decreases. When pressure decreases, volume increases. Not roughly, not relatively, but according to a precise and repeatable relationship. That result was later written simply as the formula any physics student knows. Pressure times volume equals a constant. PV equals constant, as long as temperature is constant. That is the whole idea. If you decrease pressure, volume must increase. If you increase pressure, volume must decrease. Gas does not negotiate with you. It does not care who you are, how old you are, or how much your knee hurts. It simply obeys the law. And this is what I want you to hold firmly. The law of Boyle is not a loose hypothesis or a pretty speculation from the history of science. It is foundational. It has been confirmed countless times over hundreds of years. From meteorology to scuba diving to aviation to vacuum technology and pressure vessel design, there is no real debate about whether it is true. The only question is, what is it acting on inside your body? And the answer is, on the very joints you thought were simply aging. Joints like knees, hips, shoulders, ankles, and fingers are not solid soulless blocks. They are complex biological structures containing joint fluid, soft tissue, joint capsules, and dissolved gases like nitrogen, oxygen, and carbon dioxide. Some of these gases are dissolved in the joint fluid. Some may exist as tiny gas pockets or microscopic gas regions in the joint space. That is not unusual. That is completely normal. You even sometimes hear the consequence of them. When you crack your knuckles and hear a pop in many cases, you are hearing a phenomenon related to gas in the joint fluid changing state under pressure, meaning the gas was there all along. It is not an abstract idea. It is part of joint mechanics. Now imagine a weather front passing. Atmospheric pressure outside begins to drop, maybe only 10 millibars, maybe 15, maybe 20. On paper it sounds insignificant, only about 1 to 2% of total atmospheric pressure. But Boyle's law does not say it only works when the change is big enough to impress you. It works with every change. Pressure drops, then gas volume increases. So the gases inside your joints begin to expand. Not a lot true. We are not talking about giant bubbles like in science fiction movies. We are talking about very small changes, possibly only a fraction of a milliliter. But this is where human intuition often goes wrong. We think small means unimportant in an open space. That might be true. But your joint is not an open field. It is a closed cavity surrounded by the joint capsule, ligaments, cartilage, and connective tissue. It has limits. It cannot simply say, "Oh, the gas wants to expand a little more, go right ahead." No. When gas expands in a closed space, it exerts force on the walls of that space. And the walls of your joint are not inert. They are lined with extremely sensitive nerve endings, mechanoreceptors specialized to detect stretch, deformation, and pressure. Even a small change is enough for them to send a signal. That signal travels along nerve fibers into the spinal cord up to the brain, and there you do not experience it as a physics equation. You experience it as a dull ache, a feeling of tightness, an uncomfortable stiffness when you stand up from a chair, a slight throb in the knee that was not there yesterday. That is the point where physics becomes sensation. That is the point where a law written in the 17th century touches your everyday life. And I think there is something very interesting here. For many years, many people were told that this feeling is only due to age, or because you think so, you feel so. But if there is gas in the joint, and gas obeys Boyle's law, and atmospheric pressure really drops before the weather changes, then your joint reacting is not a psychological mystery. It is a physical consequence. No superstition needed. No belief needed. Just gas pressure, volume, and a closed joint cavity are enough. And that is only the first mechanism, because at the same time the gas is expanding, something else is happening in the joint fluid. If you think the whole story stops at a little gas in the joint, expanding according to Boyle's law, then step back one more time and look at what is pressing on you from outside, because the origin of all this lies in something very basic. The atmosphere never stands still. We often talk about air as if it is an invisible backdrop, something always there and not worth worrying about. But from a physics perspective, the atmosphere is a gigantic dynamic fluid system, an ocean of gas surrounding the planet, always churning, always reorganizing itself, always changing from hour to hour. It is governed first by energy from the sun, because the sun does not heat the earth evenly. The equator receives more radiation than the poles. Land heats faster than oceans stay, differs from night, summer differs from winter, and all those temperature differences create density differences in the air. Warm air expands, becomes lighter and rises. Cold air contracts, becomes heavier and sinks. That alone is enough to create motion. But the earth is also rotating, and that rotation bends those flows through what physicists call the Coriolis effect. The result is that the atmosphere does not simply rise and fall. It swirls, deflects, organizes into high pressure and low pressure systems, into cold fronts, warm fronts, into continental scale air. Currents you see every day on weather maps. A high pressure system is usually associated with sinking air, clearer skies, and more stable conditions. A low pressure system is usually associated with rising air cloud formation, increasing humidity, and the possibility of rain and storms. That is not just weather language on TV. That is fluid mechanics on a planetary scale. And when such a system passes over where you live, the pressure at ground level really changes. It is not your imagination. It is measured by barometers, in hectopascals, in millibars. A relatively strong weather front can drop pressure by 10 to 20 millibars in just a few hours, sometimes more if the system is large and fast enough. Now on paper 10 or 20 millibars sounds like nothing compared to 10, 13 millibars of standard sea level atmosphere. It is only about 1 to 2%. If you look at it as an abstract number, you might say, is that all? But that is how intuition often misleads us. Biology does not work on small percentage so insignificant. The human body is an extremely sensitive system to pressure differences, temperature, and environmental composition. Just look at your ears on an airplane or your sinuses when changing altitude and you have a direct example. A very small change on the absolute scale can create a very real sensation when it acts on sensitive tissue or a closed cavity. And this is the part I want to emphasize clearly. Your body is not a rigid object. It is not like a stone lying outside indifferent to wind and rain. It is a soft system made of connective tissue, biological membranes, blood vessels, joint fluid, dissolved gases, air-filled cavities, elastic and semi-elastic structures, all pieced together in a delicate state of balance. A change from the environment does not just touch your surface and stop. It spreads into the system. When external pressure changes, the force on blood vessel walls changes. Pressure on sinus cavities changes. Pressure on joint capsules changes. Dissolved gases and fluids begin to leave their old equilibrium. Soft tissues experience different forces than an hour ago. In other words, every part of your body reacts to pressure because every part of your body is living inside that same physical environment. You cannot separate biology from physics. Biology is simply physics and chemistry organized in a more complex way. And so when the atmosphere changes, your body changes. That is not poetic. Not mystical intuition, but the inevitable consequence of living in a world where air pressure fluctuates constantly. What makes this phenomenon more noticeable in older people is not that the atmosphere hates the elderly more, but that the sensing and affected structures in their bodies have become more sensitive, worn or lost the cushioning that protected them when they were younger. But even before talking about age, the core remains unchanged. When the environment changes, what is inside you changes too. And once you accept that the question is no longer can weather affect the body, but how quickly does the body adjust and which parts adjust slowest? Because it is precisely that difference in speed, not just the pressure change itself, that is where the pain begins to show. And once you accept that the environment is always changing and your body is forced to react, the next question becomes extremely important. How quickly does your body react? Because if everything inside you adjusted instantly perfectly and in sync with the external pressure, you would never feel anything. But the body does not work that way. It is not an instantaneous system, but a collection of many subsystems, each with its own adaptation speed. And it is precisely that difference in speed that creates what I call biological lag. Let's start with the fastest system, the lungs. When atmospheric pressure changes, the air you breathe changes too, and your lungs can adjust almost immediately within seconds to continuous breathing. The gas composition in the lungs quickly balances with the surrounding environment, and that is why you do not feel short of breath every time pressure changes slightly. But not everything is that fast. Your blood, for example, needs time to adjust the concentration of dissolved gases. The process of gas diffusion between lungs and blood, and then between blood and tissues, does not happen instantly, but takes from a few minutes to tens of minutes, depending on conditions. That means even when the lungs have known about the pressure change, the rest of the body is still catching up. And then you come to even slower systems, especially the joints and joint fluid. Unlike blood, joint fluid is not rapidly circulated through a central circulatory system. It sits in a relatively closed cavity, exchanges slowly with the surroundings, and therefore any adjustment in pressure or dissolved gas composition happens much more slowly. This creates a very special time window, a period where external pressure has changed. The lungs have adjusted, the blood is on its way to adjusting, but the joints are still living in the old conditions. That is exactly the lag I'm talking about. During this time, your body is no longer in perfect equilibrium. Instead, it exists in a phase-shifted state where different parts of the system are in different physical states at the same time. And physics does not like phase shifts. When there is a pressure difference between regions, when there is a difference in dissolved gas concentration, when there is asynchrony in how tissues respond, forces begin to appear. Gas expands more in one place than another. Fluid shifts, tissues are slightly stretched or compressed. And all these effects do not happen in a mindless void, but in a system full of biological senses. It is precisely in this period of imbalance that the mechanisms we have talked about begin to show most clearly. That is when Boyle's law shows its impact most strongly in closed cavities that have not yet adjusted. That is when dissolved gases begin to leave solution in ways the system has not yet caught up with. That is when mechanoreceptors in the joints notice the change and send signals to the brain. And that is also when you as a conscious being begin to experience it not as an equation or a physical process, but as a very specific sensation, a dull ache, stiffness, discomfort. You cannot immediately point to a cause. What is interesting is that when the body finally catches up and reestablishes the new balance, that sensation may lessen or disappear, and you may not even connect it to the weather change anymore. But in that transitional moment, in that brief time when your system is chasing, the environment physics becomes perceptible. And that is exactly the moment many people describe with a very simple sentence, "It's going to rain, I can feel it in my bones." To understand more clearly what is really being affected in that lag period, we need to look closely at the structure of the joint itself, because a joint is not a simple mechanical hinge, like on a door, but a sophisticated biological system called a synovial joint. These joints, like knees, shoulders, hips, or fingers, are designed to both bear load and allow smooth movement. And to do that, they have a joint cavity enclosed by a joint capsule, inside which contains a special fluid called synovial fluid. This fluid is not simply a lubricant. It is a complex chemical and physical environment containing water, proteins, hyaluronic acid, and important for our story. It also contains dissolved gases like nitrogen, oxygen, and carbon dioxide. This is not unusual because every fluid in the body has some ability to dissolve gases, and they exist in equilibrium with the surrounding environmental pressure. But in the joint, besides dissolved gases, there is something even more interesting. Microscopic gas pockets, very small regions where gas can exist in an almost free form in the fluid or in the microstructural spaces of the tissue. You may have heard the sign of this phenomenon when you crack your finger joints and hear a pop. For a long time, people debated the cause of that sound, but a study using real-time MRI at the University of Alberta clearly showed that when you pull on a joint, a small cavity forms in the synovial fluid due to cavitation, and the rapid formation of that cavity creates the sound you hear. That means gas is not only present in the joint, but can also change state very quickly when pressure conditions change. Now let's go back to weather conditions. When external atmospheric pressure begins to drop, the dissolved gases in the synovial fluid are no longer in the old equilibrium, and the microscopic gas pockets, even though very small, begin to expand. According to the very Boyle's law we talked about, once again, we are not talking about large changes you can see, but extremely small changes happening in a tightly confined space. The joint cavity is not an open space. It is surrounded by the joint capsule, ligaments, and tissue structures with a certain elasticity, but they cannot expand infinitely. So when the gas inside expands, it has nowhere to go. It must exert pressure on the surrounding environment. And that environment is not an inert material, but living tissue, with cells, collagen, fibers, and most importantly, nerve endings, sensitive to pressure and deformation. Even a very small change in the internal pressure of the joint can cause these tissues to be slightly stretched or compressed in ways they are not used to, and the mechanoreceptors in them will immediately detect it. You do not need a large force to activate them. You only need a change from the equilibrium state your body is used to, and that is exactly what the expansion of gas causes. It changes the mechanical state of the joint, even if only a little, but enough for your nervous system to register that something is different. And when that signal is sent to the brain, you do not experience it as a gas pocket, just expanded by 0.1%. You experience it as a very familiar sensation, a mild pain, a feeling of tightness, a stiffness when you stand up or begin to move. This is the point where biological structure and physical law meet very directly. Your joint is not only a mechanical structure, it is a sensing system, and the gas inside it is not only a passive component, it is part of the system responding to the environment. When pressure changes, gas expands. Pressure changes, tissue is stimulated, and you feel it. No assumptions needed. No speculation needed, just look at the structure of the joint and how gas behaves. And it is enough to see that this is not a mysterious phenomenon, but a natural consequence of living in a world where pressure never stands still. So how does such a small physical change turn into something you actually feel a pain? A very clear discomfort. The answer lies in a sophisticated sensing system inside your body, especially two types of receptors. I want you to pay attention to mechanoreceptors and nociceptors. Mechanoreceptors are receptors specialized to detect mechanical changes, such as pressure, stretch, vibration, or tissue deformation, and they are present everywhere in your body, including in the joint, capsule ligaments, and connective tissues around the joint. Nociceptors, on the other hand, are pain receptors designed to detect stimuli that have the potential to cause damage or threaten tissue integrity, and they respond not only to extreme temperatures or harmful chemicals, but also to mechanical pressure that exceeds what the tissue considers normal. When gas pockets in the joint expand when the internal pressure of the joint cavity changes, when tissues are slightly stretched or compressed in ways they are not used to, it is the mechanoreceptors that are the first to notice that change. They convert mechanical deformation into electrical signals, a process physiologists call the mechanoelectric transduction mechanism, and these signals are then transmitted along afferent nerve fibers toward the spinal cord. If the change is strong enough or unusual enough compared to the previous equilibrium, nociceptors are also activated, and then the signal is no longer simply there is pressure, but becomes there is a problem. From the spinal cord, these signals are relayed up to the brain, passing through various processing stations, and finally reaching the areas responsible for interpreting sensation, where your brain has to make a decision. What is this? And the brain does not see Boyle's law or gas expansion. It only receives patterns of electrical signals. Based on experience, context, and how the nervous system is programmed, it interprets those signals into a subjective experience you call pain, or tightness, or stiffness. That is how physics becomes sensation. And this is the point I think is very important to emphasize. This is not imagination. This is not, you think you are in pain, so you feel pain. That signal is real, generated by real receptors, transmitted through real nerves, and processed by a nervous system that has evolved for millions of years to detect and respond to changes in the body's mechanical environment. You may not know the exact cause. You may not see the internal process, but that does not make the signal any less real. If a small pressure can make you feel something when you press your hand on a table, then a small change in internal joint pressure can do the same, only in a more subtle way. And when you put all the pieces together, from changing atmospheric pressure to Boyle's law, causing gas to expand, to the joint structure limiting space, to the activation of mechanoreceptors and nociceptors, you begin to see a very clear chain of cause and effect. No step in that chain needs assumption or belief. Each step is based on well-understood principles of physics and biology. And the final result of that chain is exactly the sensation you experience. So when you feel your knee hurting before it rains, that is not your body guessing the weather in a vague sense. It is measuring a real physical change in the environment, and your nervous system is reporting the result back in the only language it has: sensation. And once you see it this way, you will see that the pain is not a mystery, but a message. But if you think the whole story stops at gas expanding in a closed space, there is still another layer of physics quietly happening in parallel, and it is described by a law published in 1803 by the English chemist William Henry. Henry's law says something very simple but extremely powerful. The amount of gas that can dissolve in a liquid is proportional to the pressure of that gas above the surface of the liquid. In other words, when pressure is high, the liquid can hold more gas. When pressure drops, the ability to hold gas decreases, and gas will leave the solution. This is not a rare or hard to observe phenomenon. In fact, you have seen it hundreds of times without noticing. Think of a bottle of soda. When the bottle is still sealed, carbon dioxide is compressed at high pressure and dissolves stably in the liquid. Everything looks completely normal with no significant bubbles rising. But the moment you open the cap, the pressure above the liquid suddenly drops to atmospheric pressure, and immediately carbon dioxide can no longer stay in the solution at the previous amount. It begins to escape, forming countless tiny bubbles rising to the surface, and you hear the characteristic hiss. That is not a special effect of soda, but the basic behavior of gas in liquid when pressure conditions change. Now bring that image back to your body. Your blood, your joint fluid, and many other fluids in your body all contain dissolved gases, including nitrogen, oxygen, and carbon dioxide, and they have reached equilibrium with the surrounding atmospheric pressure. When external pressure drops, like when a low-pressure weather front approaches, that equilibrium is broken. The dissolved gases can no longer be held in the solution at the old level, and they begin to escape, not in an explosive way like a vigorously shaken soda bottle, but in a slower, more subtle way, while still following the same principle. Microbubbles begin to form in the joint fluid and the tissues in the places where gas previously existed in dissolved form. You do not see them. You do not hear them, but they are there occupying space, changing the microstructural structure of the environment where they appear. And when you combine this with what we have said about Boyle's law, you begin to see a clearer picture. Not only do the existing gas pockets expand, but new gas also appears in the form of bubbles from the liquid itself. This further increases pressure in already limited cavities, further increases tissue deformation, and therefore increases the signals that mechanoreceptors and pain receptors send to the brain. Everything happening here is not a random chain of phenomena, but the combination of very basic laws of physics and chemistry. Gas does not decide to escape. It is forced to escape when pressure drops, because that is how the system moves toward the new equilibrium. And when you look at your body from this angle, you will see that it is not only a biological system, but also a physical chemical system continuously reacting to the surrounding environment. Those bubbles, even though small enough that you cannot observe them directly, are still enough to change the way tissues interact with each other, enough to stimulate receptors, and finally, enough to create the sensation you perceive. That leads us to a very clear conclusion. The behavior of gas in your body when the weather changes is not an exception, but a completely normal manifestation of laws that have been understood for more than 2 centuries. If you take that principle deeper into the body, you will see that the story does not stop at a familiar example like a soda bottle, but it is happening continuously in your own blood and joint fluid. Blood does not only transport oxygen and nutrients, it also carries dissolved gases like nitrogen, carbon dioxide, and some unused oxygen, all existing in dynamic equilibrium with environmental pressure. Joint fluid is similar. It is not an inert liquid, but an environment where gases can dissolve and exchange according to very clear physical laws. When atmospheric pressure drops, like what happens before a storm, or when a low-pressure system approaches, that equilibrium is immediately broken at the micro level. Gas molecules are no longer comfortable in the solution, and they begin to separate from the liquid bit by bit, exactly as Henry's law predicts. This does not create large visible bubbles like in soda, but creates countless microbubbles, extremely small bubbles, possibly only a few micrometers or smaller, forming scattered in the joint fluid. Tissues. You do not see them, but that does not mean they do not exist. In physics, size does not determine importance. These microbubbles are still real physical entities, and more importantly, they occupy space. Every bubble, no matter how small, still has volume, still pushes surrounding molecules away, still creates local pressure in the environment where it appears. In an open system, this might be insignificant, but in a closed cavity like a joint, where space has been optimized to function in a very specific equilibrium condition, any additional volume must be resolved by exerting pressure on surrounding structures. This means that when microbubbles form, they do not simply be there, but they change the mechanical state of the entire microsystem in the joint. Collagen fibers are pushed slightly, cells are compressed or stretched, and the mechanoreceptors we talked about begin to register this change. If you combine that with the expansion of already existing gas pockets, according to Boyle's law, you will see that 2 processes are happening at the same time. One is old gas expanding, the other is new gas appearing from solution. Both increase the total gas volume in a limited space, and therefore increase the internal pressure of the joint. This is no longer a single effect, but the with small fishermalt of multiple physical effects, all pointing toward one result, changing the mechanical state of the tissue. What is interesting is that this process does not happen uniformly throughout the body, because different areas have different structures, different levels of circulation, and different abilities to exchange gas. That means some joints may react more strongly than others. Some areas may be more sensitive, and you may feel pain in one place without feeling it in another, even though the whole body is experiencing the same environmental change. When you look at the entire process continuously, from pressure dropping to gas leaving solution to the formation of microbubbles to them occupying space and creating pressure, you will see that this is not a vague hypothesis, but a very clear chain of cause and effect. This is the second mechanism, independent but complementary to the first mechanism we talked about. And when these two mechanisms work together, they begin to create a signal strong enough that you cannot ignore it. When these microbubbles appear, the story does not stop at them simply taking up space in an already limited space, but they begin to interact directly with the surrounding biological environment in ways your body cannot ignore. At the micro level, each small bubble is an interface between gas and liquid, and its existence changes the way forces are distributed in the joint fluid and surrounding tissue. This creates a very subtle but continuous form of mechanical stimulation as the bubbles gently push against neighboring structures, deforming collagen fibers, changing local pressure, and creating new tension points in the tissue. The mechanoreceptors we talked about do not need a large force to be activated. They only need to recognize that the normal state has changed, and the presence of thousands of small microbubbles in a closed cavity is enough to create that change. But the story goes even further, because the presence of gas bubbles in tissue is not only a mechanical phenomenon, it can also trigger a biological response. When these bubbles form and disappear, when they move or change size, they can cause small disturbances in the chemical environment of the tissue, stimulating immune cells and endothelial cells to react. This is not a strong inflammatory response like when you are injured, but a mild low-level inflammatory response, enough to increase the sensitivity of pain receptors in that area. Inflammatory mediators like prostaglandins or cytokines can be released in very small amounts, and even a small amount like that can make nociceptors become more excitable. That means the same level of mechanical pressure under conditions of mild inflammation will create a stronger pain signal than when there is no inflammation. This is an extremely important point because it explains why the pain sensation is not simply present or absent, but can vary in intensity depending on the state of the tissue. When you combine this with Boyle's law, the picture becomes much clearer. On one hand, the existing gas pockets in the joint are expanding, creating pressure on the joint capsule. On the other hand, dissolved gases are escaping and forming microbubbles, further increasing gas volume and at the same time triggering mild inflammation. These two processes do not operate separately. They happen simultaneously, overlapping and amplifying each other. The expansion increases mechanical pressure. The microbubbles change the microenvironment and increase nervous system sensitivity, and the result is that the signal sent to the brain becomes clearer, stronger, and harder to ignore. What is interesting is that all this happens at a scale you cannot observe directly, but its consequences completely perceptible. You do not see the bubbles. You do not see the molecules moving. You do not see the receptors being activated. But you feel the result of the entire chain of events as a very specific pain or discomfort. When you put all the pieces together, from the change in atmospheric pressure to Boyle's law causing gas to expand, to Henry's law causing gas to leave solution, to the formation of microbubbles and mild inflammation, you begin to see that this is not a simple phenomenon with a single cause. This is a multi-layered system where many physical and biological mechanisms work together, each contributing a part to the final experience. And it is precisely that combination, not any single factor, that creates the sensation you perceive. This is the point where we can say that the pain is no longer a mystery, but the direct result of many basic laws operating at the same time. To see more clearly that what is happening in your body before the weather changes is not a vague phenomenon at all, I want to take you to a much more extreme example where the same laws reveal themselves so clearly that no one can deny them: the world of deep-sea divers. Imagine a diver at a depth of about 30 meters underwater. At that depth, the surrounding environmental pressure is no longer 1 atmosphere like on the surface, but about 4 atmospheres, nearly 4 times normal. That means every gas the diver breathes, especially nitrogen, which makes up about 78% of air, is being forced into the body at much higher pressure. According to Henry's law, when pressure increases, the amount of gas that can dissolve in liquid also increases. So nitrogen begins to dissolve into blood, into tissues, into joint fluid, into places that normally contain gas, but at lower concentrations. While the diver is still deep down, this process does not necessarily cause immediate problems because the body and the surrounding environment are still in a new state of equilibrium. Nitrogen is dissolving, but it is dissolving stably, just like carbon dioxide in the sealed soda bottle. You see nothing unusual yet. But now change only one variable. The diver ascends too quickly. Suddenly the external pressure drops sharply from about 4 atmospheres down to 1 atmosphere in a short time. The body cannot adapt in time. Blood and tissues are still holding the amount of nitrogen appropriate for the higher pressure, but the surrounding environment has changed, and that is when the trouble begins. Dissolved nitrogen can no longer stay in solution at the old concentration, and it begins to escape. Not as individual harmless molecules, but as real gas bubbles. These bubbles can form in blood, in joints, in connective tissue, even in tissues around the spinal cord and brain. That phenomenon is called decompression sickness, or the bends. The name sounds almost gentle, but the consequences are not gentle at all. When gas bubbles form in joints, the diver can feel severe pain, a deep, sharp, intense, and uncomfortable pain that cannot be ignored. When bubbles appear in blood vessels, they can obstruct flow, causing tissue oxygen deprivation. When they affect the nervous system, the consequences can be dizziness, paralysis, disorientation, seizures, even death. That is why divers must ascend slowly in stages, sometimes stopping at decompression stops, to allow dissolved gas to escape safely before it has a chance to form dangerous bubbles. That is not superstition in the diving community. That is life-saving physics. And this is where the story comes back to you. You are not diving at 30 meters depth. You are not living under 4 atmospheres of pressure. You are not ascending from the ocean in a life-threatening situation. But in principle, your body is still going through a much smaller version of the same phenomenon every time atmospheric pressure drops. When a low-pressure system approaches, the pressure outside you decreases. Not as much as ascending from the seafloor to the surface, but enough to change the equilibrium of dissolved gases in the body. Nitrogen and other gases in blood and tissues and joint fluid begin to react. They do not create large, aggressive, and life-threatening bubbles like in severe decompression sickness, but they can create microbubbles, the tiny microbubbles we talked about earlier. These microbubbles do not cause vascular blockages or threaten life, but they are still enough to occupy space enough to change the micromechanics of the joint, enough to stimulate pain receptors, and enough to make you feel a dull ache before the rain arrives. This is the point I want you to pause on for a long time, because it completely changes the way you look at this phenomenon. When someone says, "My knee hurts before it rains," that no longer sounds like a vague folk saying. It becomes a shortened description of a very real physical biological process. Pressure drops, dissolved gas reacts, microbubbles form, tissue is stimulated, nerves send signals, brain interprets as pain. The same underlying mechanism as in the diver, only different in scale, speed, and level of danger. A diver with the bends is showing you the extreme version of what your body may be experiencing, in a much milder version. That does not mean the weather is giving you clinical decompression sickness, of course not. But it does mean you are living inside the same physical universe, governed by the same laws, and your body is reacting exactly the way those laws predict. When seen this way, the story is no longer about believe it or not. It is about scale. At one end of the spectrum is the diver ascending too fast and nearly losing his life. At the other end is you, sitting in the kitchen, rubbing your knee and saying the weather is about to change. The same principle, the same physics, only different in degree. And that is why I say, your body is not making anything up. It is simply experiencing a lighter, slower, and very human version of a phenomenon that physics has understood for a long time. Going back to 1889, when the Swedish scientist Svante Arrhenius put forward an extremely important idea about how physical and chemical processes depend on temperature. Arrhenius is famous for the equation describing how reaction rates increase with temperature, and what is important here is not the mathematical details, but the nature of the relationship. It is not linear, but exponential, meaning a small change in temperature can lead to a much larger change in the behavior of the system. This does not only apply to chemical reactions, but also directly relates to the viscosity of liquids, that is, the degree to which they are thick or thin. When temperature decreases, the molecules in the liquid move more slowly. The interactions between them become more effective, and the result is that the liquid becomes thicker and moves with more difficulty. You have seen this very clearly in everyday life. Honey in the refrigerator becomes very thick machine oil. When it is cold, flows with more difficulty, and even water changes its properties when temperature drops. But what few people realize is that the synovial fluid in your body also obeys the same principle. Synovial fluid is not plain water. It is a complex liquid containing large molecules like hyaluronic acid, designed to function as an effective lubricant under normal conditions. When temperature drops even by a few degrees Celsius, the microstructure of this liquid changes, viscosity increases, and lubricating ability decreases. This does not happen in a little colder, then a little thicker way, but in the way Arrhenius pointed out, the change can be faster than you expect, especially in a system optimized for a very narrow temperature range like the human body, around 37 degrees Celsius. When the surrounding environment cools, especially before weather systems bring in cold air, the temperature of peripheral areas like joints can drop a few degrees from normal, and that is enough to change the properties of synovial fluid. When the fluid becomes thicker, the surfaces in the joint no longer slide against each other as smoothly as before, but encounter more friction. Friction is not only a mechanical force, it is also a source of stimulation for receptors in the joint, and it increases the feeling of stiffness and discomfort when you move. If you have ever felt your joints hard to start on a cold morning, you have directly experienced this effect. And when you place it in the context we have built, you begin to see that this is not an independent mechanism, but another layer stacked on the previous ones. Gas is expanding according to Boyle's law. Dissolved gas is escaping according to Henry's law. Micro bubbles are forming and stimulating tissue, and now synovial fluid is becoming thicker due to the temperature drop. All of this happens at the same time. When a weather system approaches, pressure drops, temperature drops, humidity changes, and your body has to react to all those variables at once. That means the sensation you experience is not the result of a single factor, but the synthesis of many physical chemical processes happening simultaneously. When temperature drops, viscosity increases. Friction increases, tissue bears more load, and in the context where other mechanisms have already made the system more sensitive, this effect becomes even clearer. This is why many people not only say they hurt when pressure changes, but also say they hurt more when it is cold. Not because cold makes pain in a vague sense, but because cold directly changes the physical properties of the fluid in the joint in a measurable way. And when you look at it this way, you see that Arrhenius, Boyle, and Henry are not three separate stories, but three parts of the same picture, where temperature, pressure, and the state of the liquid work together to create an experience you simply call pain when the weather changes. Going even deeper into the very environment where all these changes are taking place, you will realize that synovial fluid is not a simple liquid like water you might imagine, but a biological system designed almost perfectly to optimize movement in the body. This fluid consists mainly of water, but what makes it special is the presence of large molecules like hyaluronic acid and lupersin, along with proteins, ions, and many other trace components. These molecules create a very unique property called viscoelasticity, meaning synovial fluid can flow like a liquid and also absorb force like an elastic material when needed. At normal body temperature around 37 degrees Celsius, the entire system works so smoothly that there is almost no significant friction between the cartilage surfaces, allowing you to walk, run, or rotate joints millions of times without noticing any mechanical noise inside. But what most people do not notice is that the ideal state is extremely dependent on temperature. When environmental temperature drops, especially during cold air masses that come with the pressure changes, we have talked about the temperature of peripheral areas like knees, wrists, ankles can drop a few degrees from the optimum. And here a change of about 5 degrees Celsius, not a small thing. According to what Arrhenius pointed out, changes related to temperature often do not occur linearly, but exponentially, meaning a small decrease in temperature can lead to a much larger change in the behavior of the system. When temperature drops, the molecules in synovial fluid move more slowly, the temporary bonds between them become stiffer, and the entire liquid becomes significantly thicker. You can imagine this like honey left in the refrigerator. It does not turn solid, but it flows much more slowly. In your joint, the same thing is happening, only at a more subtle scale. When synovial fluid becomes thicker, its lubricating ability decreases because the thin film between the two cartilage surfaces can no longer easily maintain smooth sliding as before. Instead, the surfaces begin to feel each other more, and friction increases. This friction is not the rough kind, like two pieces of paper rubbing against each other, but a slight increase enough to change the perception of the nervous system. When you begin to move, especially after sitting still for a while in a cold environment, you may feel the joint stiff, hard to open, or needing a few minutes to warm up before functioning normally. That is not because your joint is lazy, but because the physical conditions inside it have changed. When friction increases, the mechanical forces acting on the surrounding tissue also increase, and those forces in turn stimulate the mechanoreceptors and nociceptors we talked about earlier. This creates a resonant effect with the other mechanisms. Gas is expanding according to Boyle's law, microbubbles are forming according to Henry's law, and now synovial fluid is thickening due to the temperature drop. These three factors do not operate separately, but overlap, each making the system a little more sensitive, until the total is large enough for you to feel clearly. And that is why many people not only say they hurt when pressure changes, but also say they hurt more when it is cold. Not because cold makes pain in a vague sense, but because cold has directly changed the physical properties of the fluid in the joint, reducing its lubricating ability and increasing friction. When you look at the whole picture, you will see that the stiffness sensation you experience is not something random, but the inevitable result of a chain of very specific physical changes. Temperature drops, viscosity increases, lubrication decreases, friction increases, and finally, nerve signals increase. And when you understand that, you begin to see that your body is not a mysterious thing that is hard to understand, but a physical biological system that reacts in a very logical way to the world around. Eat. Looking at everything we have just gone through, one thing begins to emerge very clearly. This is not a story with a single cause, not the vague kind of weather changes so joints hurt, but a convergence of many different physical mechanisms all pouring into one place at the same time. First is Boyle's law. External pressure drops, gas volume increases, and that means the tiny gas pockets or gas regions in your joints begin to expand. That expansion itself creates mechanical pressure in a space that is not spacious at all. Next is Henry's law. When pressure drops, the gas is dissolved in joint fluid, and other fluids can no longer be held at the old state, and they begin to escape, forming microbubbles, very small but physically real bubbles. They do not just appear and stop. They occupy space, they push surrounding structures a little, they change the micromechanics inside the joint. Then comes Arrhenius. When temperature drops, joint fluid becomes thicker. Viscosity increases, lubricating ability decreases, and friction between surfaces inside the joint increases. Now notice the most important thing: these three mechanisms do not operate one after another. They do not wait for each other to take the stage. They happen almost simultaneously. A low-pressure weather system approaching usually does not only cause pressure to drop, but also brings cooler air, different humidity, and a series of environmental changes occurring almost at the same time. In your body, that means gas is expanding, dissolved gas is escaping, and joint fluid is thickening in the same time window. If there were only one isolated mechanism, the effect might be very small enough that you would not notice it. But when three mechanisms act on the same system together, they add up. Gas expansion increases pressure. Microbubbles add more volume and make tissues more sensitive. Thicker joint fluid makes movement harder and friction greater. Each one a little, but all pointing to one result. Your joint is no longer operating in its familiar balanced state. And that is why I keep coming back to the joint, because the joint is the ideal place for these effects to converge. It is a closed or nearly closed cavity. It contains fluid. It contains dissolved gas. It has surfaces that must slide against each other. It has soft tissue ligaments and a joint capsule. And most importantly, it has nerve endings that can sense very small changes in force, pressure, and deformation. That makes the joint a kind of biological amplifier for small environmental changes. The same pressure change you might completely miss in another organ can become a very clear sensation in the joint. This is also why one person feels knee pain, another feels shoulder pain, and someone else feels finger joints stiffen. The underlying mechanism is the same, but the specific point of convergence depends on body structure, age level of cartilage, wear history of injury, and sensitivity of each area. And this is exactly why, under normal conditions, all the small changes in pressure and gas in the viscosity of joint fluid we have talked about in previous parts do not immediately become sensations you perceive. Articular cartilage acts as a cushion, a shock absorber, a layer of isolation between the physical processes inside the joint and your nervous system. When gas expands, when microbubbles form, when joint fluid thickens, and friction increases, this cartilage layer absorbs a significant portion of those changes, disperses the force, and reduces the direct impact on more sensitive tissues below. You can think of it like a rubber cushion in the mechanical system. It does not eliminate the force entirely, but it makes the force softer, less sudden, less stimulating. And it is thanks to this cartilage layer that most of the time you feel nothing, even though the laws of physics are still operating inside your body every day. But this cushion is not perfect forever. It has limits to its durability, to its ability to recover, and most importantly, it does not self-repair, as well as many other tissues in the body, precisely because it has no blood vessels to supply nutrients directly. Over time, through millions of movement cycles, the microstructure of the cartilage begins to change. Collagen fibers can be damaged. The amount of water held in the cartilage decreases, and the originally smooth surface begins to become less perfect. This does not happen overnight, but is a very slow process, almost imperceptible from day to day, yet accumulating over many years. The result is that the cartilage layer gradually thins, loses some of its ability to absorb force and disperse pressure. And when the cartilage thins, what happens underneath begins to matter more. Beneath the cartilage is subchondral bone, and unlike cartilage, bone has blood vessels and has nerve endings. Under normal conditions, the cartilage layer covers and protects this bone from direct mechanical fluctuations. But when cartilage wears, the protective layer is no longer as effective as before. Forces that were previously absorbed and softened by cartilage now transmit more directly to the bone and surrounding tissues, where there are nociceptors ready to detect any unusual change. This means the same change in atmospheric pressure, the same level of gas expansion, the same number of microbubbles forming in joint fluid, but in a young, healthy joint with thick and elastic cartilage. You may feel nothing significant while in a joint that has gone through many years of use, where cartilage has thinned and force absorption has decreased. Those changes become more visible to the nervous system. This is not because physics changes with age. Boyle does not change. Henry does not change. Arrhenius does not change. Arrhenius does not change. This leads to a very important conclusion. Pain does not necessarily have a single cause. We often like simple explanations like knee hurts because it is cold, or pain because of low pressure. But the body is far more real than that. Pain can be the product of many small physical causes, adding up until they cross the threshold where the nervous system begins to sound the alarm. That is exactly what is happening here. Boyle alone is not enough. Henry alone is not enough. Arrhenius alone is not enough. But when all three operate together in the same joint on the same morning before the rain arrives, the picture changes completely. And I think this is the most beautiful thing about science. A phenomenon in everyday life that seems trivial and full of folk wisdom turns out to be the place where three basic laws of physics and chemistry intersect. So when someone says they feel the weather in their bones, I no longer hear a sentimental statement. I hear a fairly accurate description, even if not in technical language, of a mechanical system reacting to the environment. That pain does not come from nowhere. It does not appear because of imagination. It is the result of changing pressure gas, expanding gas, leaving solution joint fluid, thickening friction, increasing tissue being stimulated, and nerves sending signals. One single sensation, but behind it many physical causes converging. And it is precisely that convergence that makes this phenomenon so convincing. If all these physical mechanisms are happening continuously in the body, why do you not feel them all the time? Why does the pain only become clear under certain conditions? The answer lies in a structure you rarely think about, but it serves as a perfect cushion in your joint articular cartilage or cartilage. This layer of cartilage covers the ends of bones and synovial joints and has an average thickness of about 2 to 4 millimeters. It sounds very thin, but functionally it is one of the most effective biological materials nature has ever created. Articular cartilage has a special structure of collagen networks and proteoglycans that hold water and create a surface that is both flexible and durable, allowing it to absorb force and disperse pressure extremely efficiently. When you walk, run, jump, or even just stand still, the force acting on the joint can be many times your body weight, and it is this cartilage layer that is responsible for smoothing those forces, turning mechanical impacts into evenly distributed pressure changes. But the most interesting thing about articular cartilage is not its durability or elasticity, but what it does not have. Articular cartilage has no blood vessels, and more importantly for our story, it also has no nerves. That means the cartilage itself cannot feel pain. It does not send signals to the brain when it is compressed, stretched, or loaded. What changes is how your body cushions those effects. When the cushion weakens, what was once hidden now becomes noticeable. And that is why the phenomenon of weather-related aches is often reported more in older people or those with a history of joint injury. Not because physics changes with age, but because their biological shock absorber no longer works as effectively as before. When cartilage is no longer thick or elastic enough to absorb force, every small fluctuation in the physical environment inside the joint becomes clearer to the nervous system. And this is a very important point. To understand pain does not necessarily mean something abnormal is happening in a pathological sense. It may simply be normal processes becoming more noticeable because the protective layer has weakened. When you place this into the overall picture, you begin to see a very coherent logical chain. The environment changes physical laws, trigger processes in the body, and the structural condition of the joint determines how much you perceive those processes. Age in this case is not the direct cause of pain, but a factor that changes the sensitivity of the system. A young joint can absorb and soften those fluctuations before they reach the nervous system, while a worn joint allows those fluctuations to go straight to the pain receptors. So when an older person says they feel the weather in their bones, that is not an exaggeration, but a fairly accurate description of how their biological protection has lost effectiveness, making the physical processes that have always existed clearer in daily experience. And in that sense, pain is not a random sign of age, but the result of a system that has operated long enough to become more sensitive to the world around it. Another layer of perception in the body that most people do not think about immediately when talking about pressure, but plays a quiet yet extremely important role in this story, is the baroreceptors. Pressure sensors located deep in your cardiovascular system. These receptors are not in the joints. They are not directly related to joint fluid or gas in the joints, but they are part of the larger system the body uses to measure pressure and maintain internal stability. Baroreceptors are mainly located in two strategic places: in the carotid arteries in the neck, where blood is delivered to the brain, and in the aortic arch, where blood leaves the heart to go throughout the body. These locations were not chosen randomly because they are the points where blood pressure directly reflects the state of the entire circulatory system. Baroreceptors work by sensing the stretch of blood vessel walls. When pressure inside the vessel increases, the wall stretches more, and these receptors detect that change. When pressure drops, the wall contracts and the signal changes accordingly. What is astonishing is that they can detect extremely small changes, sometimes under 1% of pressure, a level of sensitivity that, if you think about it, is almost beyond ordinary intuition. When baroreceptors detect a change, they do not just record it. They immediately send signals to the brain, specifically to regulatory centers in the brainstem, to adjust the activity of the cardiovascular system. The heart may beat faster or slower, blood vessels may constrict or dilate, all aimed at keeping blood pressure stable within a very narrow range. This is a continuous feedback system operating every second, every minute, without you noticing. But what is interesting is that this system is not completely isolated from the outside environment. When atmospheric pressure changes, especially when it drops during low-pressure weather systems, it can indirectly affect pressure inside the body, even if the degree is not as large as in diving. Baroreceptors can sense these subtle changes and trigger corresponding adjustment responses. That means your body is not only reacting at the mechanical level in the joints, but but also at the systemic level through the autonomic nervous system and the cardiovascular system. You may not notice these adjustments clearly, but they can contribute to the overall sensation you experience, such as mild fatigue, slight dizziness, or a hard-to-describe punees. And when you place this into the overall picture we have built, you will see that your body is not just a passive system affected by pressure, but an active system continuously measuring, reacting, and adjusting to maintain balance. The joints react to mechanical changes, the fluids react to chemical and physical changes, and the cardiovascular system reacts through baroreceptors to keep the whole system stable. This leads to a very important conclusion. Your body is not affected by weather in a passive sense. It is continuously interacting with the environment, reacting to the smallest changes to maintain internal stability. And in that process, some signals become strong enough for you to notice, especially when other systems like the joints have become more sensitive over time. So when you feel your body off before the weather changes, that is not just a single sensation, but the result of many sensing and regulatory systems working at the same time. Photoreceptors are only one part of that network, but they show one thing very clearly: your body is not blind to environmental changes. It is measuring them continuously with astonishing accuracy, and reacting in ways you can feel even if you do not always understand the cause. There is an experience that many people recognize but rarely describe with real precision. It is not a sharp pain, not a clear signal like when you are injured, but a spreading feeling of fatigue, a heavy, sluggish, slightly uncomfortable state, as if your body is reacting to something your consciousness has not yet named. You wake up in the morning and feel a little slower than usual. Your limbs are not in severe pain, but they seem heavier. Your mind is not exactly dizzy, but a bit foggy. Your mood is not exactly bad, but not really comfortable either. A very hard-to-grasp feeling of unease, hard to explain, but real enough that you know something is different today. And I think this is one of the most interesting parts of the story, because if you only look at joint pain, you might think the body only reacts at one very specific point. But no, when the weather changes, the body does not react only in the knees or wrists. It reacts as a system. That fatigue is not imagination. It is physiology happening at the whole body level. To understand this, you have to go back to the autonomic nervous system, the part of the body that works day and night without ever asking your opinion. It controls heart rate, blood pressure, breathing, vascular tone, fluid distribution, peripheral temperature, digestion, and a host of other processes you only notice when something goes off. This system works like a continuous governor, always receiving signals from the outside environment and the inside environment, then adjusting variables to keep the body in a stable state. Now imagine a low-pressure system approaching. Atmospheric pressure begins to drop. Temperature may fall along with it. Humidity changes. The baroreceptors we just talked about detect the very small change in pressure acting on vessel walls. The autonomic nervous system receives that signal and begins to do what it always does: adjust. Blood vessels may constrict or dilate differently. Heart rate may change subtly. The way blood is distributed between periphery and core may shift. Breathing may change slightly without you noticing. It sounds trivial, but the problem is that all those changes consume energy. Your body does not just sit there and let the world happen. It is continuously reacting to keep you stable, and each time it reacts like that, the system has to work. This is the point many people miss. We often only count fatigue in mechanical terms. You walk far, you exercise hard, you lack sleep, so you are tired. But there is another type of fatigue, much more subtle fatigue, from physiological adjustment. When the body has to continuously fine-tune blood pressure, heart rate, vascular tone, blood flow, and baseline nervous state, it is expending resources even if you are not getting up to do anything. So you can have a day where in terms of activity you did nothing special, but you still feel drained of energy. Not because the body is lazy, not because you are weak, but because part of the energy is being used for adaptation. And this goes further than pure energy expenditure. The autonomic nervous system has a very tight connection with your subjective feeling of comfort or discomfort. When this system runs smoothly, you almost do not think about it. But when it has to work harder than usual, or when it is pushed into a state of continuous adjustment, you may begin to feel something very hard to name. Not exactly anxiety, Not exactly pain, but a state of slight bodily unease. You do not necessarily think my heart has a problem or my blood pressure is changing, but you feel that you are not in the familiar balanced state. This is completely consistent with physiology. When baseline regulatory systems are shifted, your subjective experience changes too. And that is why so many people say that before the weather changes, they not only have pain, but also feel off, feel heavy, feel drained. Those folk phrases, if you translate them into physiological language, are describing an autonomic nervous system that is compensating, a cardiovascular system that is self-adjusting, an internal environment that is trying to maintain balance while the outside environment has just shifted. What I find beautiful here is that you do not need to choose between joint pain and fatigue as if they are two unrelated phenomena. They are two different expressions of the same event, the body reacting to environmental fluctuation on multiple layers at once. The joints react mechanically. Joint fluid reacts chemically and physically. Tissue reacts through low-level inflammation. The cardiovascular system reacts through baroreceptors. The autonomic nervous system reacts by adjusting the baseline state of the whole body. And the final result you experience can be a mixture of all of that: mild pain in the knee, heavy head, sluggishness, lack of energy, vague discomfort. Nothing in it is made up. Nothing in it is just because you are overthinking. It has a clear physical and physiological basis. What makes it hard to grasp is only that it does not manifest in a loud way, but in a diffuse and subtle way. But subtle does not mean unreal. On the contrary, many of the most important processes in the body are always subtle. And once you understand that, you will look at your naturally feeling off days with a different eye, not as a failure of the body, but as proof that it is continuously reading the world around it, continuously calculating, continuously adapting. That fatigue, that unease is not a vague mystery of age or weather. It is physics passing through physiology, then becoming conscious experience. And once you see the thread connecting those three layers, you will no longer easily call it imagination. There is another place in the body you may not think of immediately when talking about pressure, but it is extremely sensitive to it. The sinus cavities in your skull. These sinuses are not meaningless empty spaces, but air-filled cavities located in the skull bones, including frontal sinuses, maxillary sinuses, ethmoid sinuses, and sphenoid sinuses lined with mucosa and connected to the nasal cavity through small tubes. Normally, these cavities are continuously ventilated, and the pressure inside them balances with external pressure through these passages. When everything works smoothly, you are completely unaware of their existence. But the problem begins when atmospheric pressure changes quickly, especially when it drops before a low-pressure weather system and the body cannot balance the pressure in the sinuses synchronously. If these small passages are narrowed, slightly inflamed, or simply do not adjust fast enough, the pressure inside the sinuses and outside begins to differ. And because these sinuses are closed air-filled cavities, the pressure difference creates force on the sinus walls, on the mucosa, on the surrounding tissues. This is very similar to what we have said about joints, but in a different location and with a different structural system. This pressure difference can stretch or compress the tissues in the sinuses, and more importantly, it stimulates the nerves in that area, especially branches of the trigeminal nerve, one of the largest. Sensory nerves in the head. When these nerves are stimulated, signals are sent to the brain, and you perceive it as a headache, pressure in the forehead, behind the eyes, or across the cheeks. This is not an imagined pain, but a direct response to a physical change in an air-filled cavity in the body. In fact, there have been studies that have examined this connection systematically. A study published in 2015 in the journal Internal Medicine recorded that changes in atmospheric pressure, especially drops in the range of 6 to 10 hectopascals, are associated with an increase in migraine frequency in some sensitive people. That number, if you remember, falls in the same range we talked about for pressure changes when a weather system passes. That means what you feel is not just personal experience, but also consistent with data observed in research. What is interesting is that not everyone reacts the same. Some people have clear sinuses and adjust pressure very well, so they feel almost nothing. Others, possibly due to anatomical structure, mild sinus inflammation or higher nerve sensitivity, will feel the difference more clearly. And when you place this into the overall picture we have built, you begin to see that this is not an isolated phenomenon, but part of the same principle. Air-filled cavities in the body react to pressure changes. In the joints, you have gas expansion and microbubbles. In the sinuses, you have air temporarily trapped in a closed cavity, creating a pressure difference. In both places, the final result is mechanical stimulation of tissue and nerves, and from there, the creation of sensations you perceive. So when you feel your head heavy before it rains, or have a dull ache around the forehead or behind the eyes, that is not a phenomenon separate from what is happening in your joints. It is the same story, only happening in a different location. And if you have been following the entire chain of reasoning, you can see that we have gone through many different mechanisms. Gas expansion according to Boyle, dissolved gas escaping according to Henry, joint fluid changing according to Arrhenius, the autonomic nervous system adjusting through baroreceptors, and now the sinus cavities reacting to pressure differences. This is the fourth mechanism in the overall picture, and it completes another important piece. Not only the joints, but also the air cavities in your head are feeling the weather in a very physical way. When you look back at the entire journey we have just gone through, from the dull aches in the joints to the feeling of a heavy head fatigue and spreading discomfort, a picture begins to emerge with surprising clarity. These are not separate phenomena, but different expressions of the same physical principle acting on multiple systems in your body at the same time. First is the joint system, where closed cavities containing fluid and dissolved gas react to pressure changes through Boyle's law and Henry's law. Gas expands, microbubbles form internal pressure changes. Tissue is stimulated and mechanoreceptors send signals to the brain. Next is the fluid system, where joint fluid and other biological fluids change properties when temperature drops according to the principle described by Arrhenius. Viscosity increases, lubricating ability decreases, friction increases, and movement becomes less smooth, adding another layer of mechanical stimulation to the system. At the same time as the nervous system, especially the autonomic nervous system, and baroreceptors continuously measuring and adjusting internal pressure in the body, reacting to very small environmental changes. These adjustments consume energy. They change the baseline state of the body and create feelings of fatigue, sluggishness, or unease you may notice on days when the weather fluctuates. And finally is the sinus system, the air-filled cavities in the skull, where pressure differences can directly create pressure on tissue and stimulate nerves, leading to headache or forehead heaviness. These four systems, which on the surface seem unrelated, are actually reacting to the same variable, the change in pressure and temperature in the environment. What makes the story interesting is not each mechanism alone, but the way they overlap, interact, and converge in the same time window. A pressure drop of a few percent, temperature drop of a few degrees, a change in humidity. All of that may seem insignificant if you look at each factor separately. But when they occur simultaneously in a sensitive biological system optimized for a balanced state, they create a chain of reactions spreading through many layers of the body. And at each layer, from mechanical to chemical to nervous, the signal is amplified a little, until the combination becomes an experience you can clearly recognize. This is the point I think is very important to emphasize. Nothing in this story is mysterious in the scientific sense. There is no invisible force, no supernatural mechanism, nothing outside the laws that have been understood for hundreds of years. Boyle, Henry, Arrhenius, neurophysiology, fluid mechanics, all of them have been there, and your body is simply a place where those laws operate together. What makes this phenomenon seem mysterious is only that it happens at a small scale in many places at once and is experienced through subjective sensation. You do not see molecules moving, you do not see pressure changing in each cavity. You do not see electrical signals running in nerves. You only feel the final result. And because that result is personal, because it is sensory, it is easy to assign vague explanations to it. But when you peel back each layer, when you connect the mechanisms together, you begin to see that this is a very logical system. Each part has its role. Each response has a specific cause. And when all those parts operate at the same time, you have a phenomenon that humans have recognized for a long time, but have only recently begun to understand more clearly. Your body is reacting to the weather in very physical ways. So when someone says they feel the coming rain in their body, that is no longer a metaphorical or superstitious statement. It is a short description, not precise in technical terms, but correct in essence, of a biological system interacting with the environment according to the laws of nature. And once you see it that way, you will see that the wonder is not the pain or discomfort, but the fact that your body can sense very small changes in the surrounding world through mechanisms so subtle that you only notice them when they are strong enough to cross the sensory threshold. And now when you or someone else says, "My knee is starting to ache, it must be about to rain," you will see that statement no longer sounds vague. You have gone through a long journey from atmospheric pressure, from Boyle's law, Henry's law, Arrhenius, from the structure of the joint fluid, from the nervous system, from baroreceptors, from microbubbles to the sinus cavities in the skull, and you begin to see that your body is not separate from the world around it. It is not a closed system. It is not a machine operating independently. It is part of the environment, continuously exchanging, continuously adapting, continuously reacting to changes, even very small ones. You do not need a big storm for the body to react. Just a pressure drop of a few percent, a temperature change of a few degrees, a shift of air in the atmosphere, and a series of processes inside you begin to change. Gas expands. Gas leaves solution joint fluid, thickens friction, increases tissue, is stimulated. Nerves send signals. The cardiovascular system adjusts. The autonomic nervous system expends energy to maintain balance. The sinus cavity sends pressure differences, and all of that converges into an experience you simply call pain, fatigue, or discomfort. What is interesting is that, for a long time, many people were told that these sensations are only subjective, only psychological, only because you think too much. But when you look at the whole picture, you see that there is a very clear physical foundation behind it. That does not mean every detail has been fully understood, or that everyone will react the same. The human body is a complex system, and each person has different structure, different sensitivity, different injury history, different health state. Some people feel almost nothing when the weather changes. Others feel it very clearly. Some only feel joint pain. Others feel fatigue, headache, or a spreading discomfort. And there may still be other mechanisms we have not fully understood, small details that science is still exploring. So I do not want to end this story with an absolute statement like, "This is the complete answer." Science rarely works that way. But I think we have gone far enough to see that this phenomenon is not something mysterious. It is a very beautiful example of how basic laws of physics and chemistry, things written down hundreds of years ago, are still operating in every cell of your body, every day, every hour. And perhaps the most interesting thing is not that we can explain it, but that you have always experienced it without needing to know the equations or laws behind it. Your body knew before you understood. It has reacted to the surrounding world in a very precise, very consistent way. It is just that you did not yet have the language to describe it. And now, with an additional perspective perhaps, the next time you feel a mild ache before the weather changes, or a hard-to-explain feeling of fatigue, you will no longer see it as something random. You can see it as a signal, a sign that your body is interacting with the environment in subtle ways you rarely notice. And I think that is a very different way of looking at it. Not that your body is bothering you, but that it is showing you that you are not separate from this world. You are part of it, influenced by the same forces, the same laws, the same fluctuations. And if you think about that for a moment, it is quite interesting. Because that means you do not just live in the weather, you are experiencing it from the inside. You may not predict the weather, but you are feeling it. If you find this way of looking at things changes how you understand your body, please subscribe to the channel so you do not miss the next interesting science stories. Thank you for watching, and I will see you in the next journey of discovery.